nanohub.org.
Online simulation and more for nanotechnology.
Today we are going to talk about Gaussian process regression, which is the most powerful regression method that just works most of the time without really worrying too much about it. There are other regression methods that are even more powerful, but they're a pain in the butt to actually train. This really, it's one of the best, it's the best regression method that automatically gives you the correct error bars, that automatically finds the right hyperparameters for you, and you just feed it X and Y's and it just works, and there's really nice code for it. And it is based on the idea of a probability measure on a function space that we introduced before, on the idea of using a Gaussian process to define such a probability measure. And we'll talk about it. Okay, but so even though this goes a little bit, I'm not even going to mention it. Right? So today we're going to talk about using Gaussian processes to do regression. Just as a reminder, we used Gaussian processes last time to define the probability measure on a function space. And that probability measure captured our uncertainty about functions, basically, about some functions of our models. And so we're going to exploit this idea to do regression. I'll tell you how in a while. And I'll give you a way to find the hyperparameters of the mean function or the covariance function using data. And the last part, we're not really going to do it because I don't think we're going to have time, because I want you to play a little bit with the handout. Anyway, so this is the best book on the matter. It's actually, you can find it online for free. What you should really read from this book is chapter 1, and then chapter 2, and perhaps 4 and 5. Okay, and then you should stop there. But so last time, actually, yes, these 4 chapters are enough to use this thing in your own work. You should be able to do regression with your own data, and then just based on these 4 chapters, write about the theory. But anyway, there is excellent code by University of Sheffield and Neil Lawrence in particular. The code is called GPy, and this is what we're going to be using. And let me give you a reminder of what a Gaussian process was. We talked about this last time. So imagine that you have a function f, has some inputs x, some outputs y, but you are now uncertain about that function f. You don't know what it is. Okay, so that function f could be a function that is on which your model depends, or it could be your model, the model itself. Okay, but it's a function that you don't know, and we're going to use Gaussian processes to put to treat f as unknown and put a probability density on the space of functions. So the Gaussian process basically allowed us to introduce this idea, the idea of a probability measure on a function space. Okay? And we said that the Gaussian process needs 2 ingredients. One is a mean function, and the mean function specifies any trends of that unknown function. So you know that that function should be a little bit linear. You add that on the mean. If you know that it does a crazy exponential decay thing with some oscillations, you add that on the mean function, and so on and so forth. So the mean function is what you think the function values are before you see any data. That's what it should be, or before you see any more data. And if you have absolutely no idea what it is, you can just pick it to be 0. And the covariance function is the second ingredient, and that covariance function is a function of 2 things, an x and an x prime, and it tells you, it quantifies the similarity of the function values at 2 different input points. So covariance function evaluated at x and x prime tells you how likely the values of the function x and x prime, how likely it is that they are similar. The bigger the covariance function is, the more similar, the more correlated the function values are going to be. The smaller the covariance function value is, smallest could be 0, or even a little bit negative. It could be a little bit negative. The less correlated the function outputs are going to be. And this is basically an extension of the multivariate Gaussian, right? So we said that at the time, the multivariate Gaussian needs a mean vector. This needs a mean function. Multivariate Gaussian needs a covariance matrix. This needs a covariance function. So if you like, it's a generalization of the multivariate Gaussian to an infinite dimensional space that happens to be a function space. All right. And we're going to be writing this for the Gaussian process. So we'll say that this unknown function f, before we see any data, we think that it is a sample from this probability measure, and we read this a Gaussian process with this mean and that covariance. And it looks, samples from the Gaussian process look like that. I mean, its instant of this video is a 5 samples, okay, and it's just moving around to visualize them, okay, but its instance is 5 samples. And remember that we said that the covariance function can control the regularity of these functions. You can, there is a place where you can talk about the length scale of these functions. You can make the length scale small and you'll see them becoming more wiggly. You can make the length scale greater and you will see them becoming flatter. There's a place where you can control the variance of these functions, how far up and down they go. You can also control how smooth they are. You can say, I want functions that are continuous, nowhere differentiable. I want functions that are twice differentiable. I want functions that are an infinite number of times differentiable. This is what happens here. You can actually ask for functions that are periodic, etc., etc. All right. So, and all this goes inside the covariance function. So the covariance function, you can use it to specify what you know about this thing before you see any data. Right? So now what we're going to do is we're going to say, okay, we have already specified what we know about the function before we see any data. Let's now see some data. Okay? And update our beliefs about these functions. And this is the first version of our Gaussian process regression. So we have a bunch of observations, and let's assume for the time being that there is no noise. We can evaluate exactly f of x of that unknown function. I mean, there is an experiment that we can do. It's going to give us the value of f of x exactly without any noise. Okay? And we gather a bunch of data points. At x1, we go and we evaluate, we do our experiment and we get f of x1. At x2, we get f of x2. And at xn, we get f of xn. And these values are exact. Okay? And we wish to learn f from these values. Alright? But we're gonna, instead of just, coming up with a generalized linear model and try to train it and all that, we're going to do the following thing. We're going to say that Gaussian process that we introduced the last time, it represents what we know about the function before we see the data. So now let's see some data and condition this probability measure so that samples from it go exactly through these observations. This is what we're going to do. Okay, so samples from this probability measure are compatible with what you know. They have the right length scale, they have the right variance, they have the right smoothness. And now you're going to say, out of all these functions, I really only want to keep the ones that go through the data points. Okay? And of course, there's more than one that goes through the data points. And this is how it's going to look like. So on the left, you see your prior Gaussian process, which is supposed to be what you think about this function before you see any data. And here, the assumptions that we have encoded are the following. First, the function I'm looking for is infinitely differentiable. It has derivatives up to any order you like, and they're all continuous. Okay, that's the first thing we have encoded here. The second thing that we have encoded here is that the length scale of this function is about 0.2. Meaning that you need to go 0.2 to see it do, one full up and down, one full wave. Alright? Approximately. It's definitely, smaller than 0.5 and a little bit bigger than 0.1. And the other thing that we have said is that the variance of this function is 1. Meaning that with 95% probability, it is plus or minus 2 square root of the variance, which puts it with 95% probability between minus 2 and 2. Of course, this may be the wrong, maybe a wrong assumption, but it doesn't matter because the data is going to correct it later on. But anyways, to wrap it up, we're assuming that it is infinitely differentiable. We're assuming a length scale of about 0.1, okay? And we're assuming a variance of about 1. But of course, in your case, you could have a variance of about 10 or a different length scale and so on and so forth. And you can always say something about these functions before you even look at any data. All right, so with that information, we built this prior Gaussian process. And then we're going to do the following thing. We're going to observe that function at 1, 2, 3, 4, around 10 points. Okay, so we have about 10 observations. And at its crosshair, you see one observation, right? So an X and a corresponding Y. And we're assuming that there's absolutely no noise. The observations are perfect. So you know what we're doing here? We're basically going to this space where we have these functions, and we say, okay, we have an observation here. Let me just grab these guys and hold them there so that they go through X and Y. Let me also grab them here. So you grab them there. And of course, in between, they can do crazy things, but they're going to have to go through the data points. So that's exactly what you do. And the way you do this, you don't obviously do it with your hands. You do it with Bayes' rule. Okay? So let's do it. It's going to be a little bit ugly. Okay? But at the end, it will result in a very nice formula. All right, so here we go. We have observed this X and the corresponding function values. And now let's do the following exercise. Because remember, a Gaussian process, it's actually probability measurement functions, but it's an infinite object. You cannot really work with it. You're going to have to work with something discrete. So to make everything nice and discrete, we're going to do the following thing. We're going to say, here's my data, this X and the corresponding values F. Now, instead of trying to come up with a Gaussian, to restrict this probability measure as a probability measure on a function space, let me do the following thing. Let me just say, I will just look at a finite number of input points. I'll just look at these input points. I'm going to call them X star. I'm just going to ask questions about the function values at these input points X star. So I say, forget about the whole function space. Let me just concentrate on some points X star. But of course, these X star points are arbitrary. Could be anything you want. I mean, you can pick one of them, you can pick two of them, you can pick 10,000, and you can pick them in any way you like. But let's start by making them nice and finite. Okay, so that's the trick. And then we're going to use the definition of the Gaussian process. The definition of the Gaussian process says that if you take any number of input points and you consider the function values at these input points, the function values will be distributed according to a Gaussian with a mean vector that comes from your mean function and a covariance matrix that comes from your covariance function. So you can now consider the joint probability density of the observed Fs, the observed outputs, and the outputs on the test points, which are completely arbitrary. So you can consider the joint density of both your observed outputs and some hypothetical outputs on which you may want to evaluate your function. Yes?
So the hypothetical outputs, were those chosen arbitrarily and now you're seeing how well they match?
Right now, they are completely arbitrary because we're trying to do a proof. Without me telling you that we're really true. I should have probably started from the theorem that I'm trying to prove, but so now these hypothetical outputs, they correspond to some hypothetical inputs that are completely arbitrary. And the only reason I introduced them is so that I discretize this function. Instead of working with a function, I'm just going to work with the function values at an arbitrary set of inputs. That's the idea. But anyway, let me just give you this picture how this probability density it really looks like. It's first of all, it is a finite dimensional probability density. It corresponds to a finite dimensional random value f and f star. Of course, f is observed, but we'll enforce that in a while. This m here is the mean function evaluated at the observed inputs. The m star is the mean function evaluated at the test inputs or the hypothetical inputs, okay, which are arbitrary. And then the covariance matrix consists of 4 blocks. This block right here is the covariance matrix of your observed inputs. Okay, so it's the covariance function evaluated at all pairwise combinations of the observed inputs. This diagonal term at the bottom is the covariance function evaluated at all pairwise combinations of the test inputs. Okay, so it's just like this guy, but this guy uses the test data. And then these are the cross covariance terms, observed inputs with test inputs together, all possible combinations again of these two. And this is the transpose of that. And this is just the theory. So the theory says that if you have a Gaussian process on the space of f's, and you want to know f at a finite number of points, then this is the distribution it should you should pick. This is the definition of this probability measure on the function space. Anyway, so you have that, you have the joint distribution, but now you're actually observing something. That f at the top is observed. So you want to take that joint distribution and condition on f and ask a question about f star. This is what you're going to do. So you want to ask, what do I think f star is if f is observed? This is the question I want to ask. And to answer this question, you use Bayes' rule. And it turns out that if you use Bayes' rule, and this is going to be a homework problem, mark it. But it's again on Bishop, so it's really not a homework problem. It's just you reading again 2.3 of Bishop. Okay. So there's a theorem that can that tells you if you have a multivariate Gaussian and you observe part of it, how can you get the conditional distribution of what remains? And this is the theorem that we're using. So if you have the joint Gaussian process on the multivariate Gaussian on the top, and you observe f, and you want the posterior of f star, which is this thing right here. What do you think about f star if you have seen f? Then this is also going to be Gaussian. So if you condition a multivariate Gaussian, you get a Gaussian. I think you could guess that because everything you do to a Gaussian, it results in a Gaussian, okay? And it's a special Gaussian with a mean and a covariance matrix that is a little bit different than before. And this is how this mean and covariance matrix looks like. So it's, if you look at the mean, the posterior mean, it's going to be the prior mean, that m star that you have up there, but it's going to be corrected by something that depends on the data that you have seen. And if you look at the covariance matrix, the posterior covariance matrix is going to be your prior covariance matrix correcting by something that depends on the inputs that you have seen. Okay? Now, because the selection of, and this is where the mathematical proof concludes, because the selection of these test points was completely arbitrary. I mean, you could pick how many you want, you could pick where they are, completely arbitrary. This actually gets us back to Kolmogorov's theorem and guarantees the existence of a posterior Gaussian process, a random field, a posterior random field that is compatible with both the data and your prior state of knowledge. And that posterior random field is also a Gaussian process. Okay, so you started with a Gaussian process, you made a bunch of observations, and Bayes' rule gave you, I mean, admittedly with 10 minutes of me waving my hands, but that's exactly what happens. Started with a prior probability measure, Gaussian process, you observe some input-output data, and Bayes' rule gave you a posterior Gaussian process. It gave you also a Gaussian process. And that Gaussian process is this Gaussian process with its own mean function and its own covariance function. And if you look at the mean function, is the mean function you started with plus a correction. That depends on your data. Alright, so you see your observed outputs go there. And this is your covariance function, which is a correction of your previous covariance function, which is just this, and corrected by this quantity right here. Okay? I know that doesn't make sense, but you'll see it. Okay? Yes?
Since we are choosing the function values that of the test input arbitrarily, how can we rely on the covariance function that's there?
So the test function outputs disappeared. Do you see them anywhere? No.
But the covariance matrix depend on the test function value.
No. This is the prior covariance matrix. This is the covariance matrix on just the observed inputs. Everything here is observed. This is basically K, capital X inverse. So it's the covariance matrix evaluated on all pairwise combinations of your observed data. This is what it is. This guy. So everything here is observed. The only reason we introduced the test points is so that it's because we cannot really condition a random field, a probability measure in a function space, because it's an infinite object. We're going to have to work with a finite dimensional objects, but of arbitrary dimension and arbitrarily built. That's how you prove that when you condition a Gaussian process on some data, you get also a Gaussian process. Now, why exactly this happens? You probably need to go and take a math course on random fields. Beyond what I want to do, I would spend like 2 weeks on just that. It's because we're working together, you should probably take it. Okay? Alright. Let's look at some practical examples of this. So this is what happened here. Okay? This is what happened here. I started from this Gaussian process, and then I said, give me an arbitrary number of test inputs. Pick 1,000 inputs. I will consider the values of f on these 1,000 points. The joint distribution of these 1,000 points plus the values of the function of the observed inputs, it has to be Gaussian. Then I'm saying, let me use Bayes' rule. I have like 1,010 dimensional random vector, and I'm just observing 10 components of it. Let me use Bayes' rule to derive the posterior. So you derive the posterior, and just by observation, it looks like a Gaussian process with a special covariance and a special mean. But anyway, in reality, once you grasp, what you need to grasp is that you start from a prior probability measure, and then you grab the points where you want your functions to go through. You just grab your functions, you force them to go through these points, and then you get a posterior probability measure. And if this is a Gaussian process, that is going to be a Gaussian process. And if you know the mean and covariance of that, then there's a formula for the mean and the covariance of that. And as a matter of fact, you don't even have to worry about the formula because the formula is already implemented in ZPy. Okay? So, even though the Gaussian process is one of the most complicated topics I'm going to introduce in this class, and it's really not easy to understand. It probably took me like a year to understand what it is. Nevertheless, it is one of the most powerful. It works most of the time as expected. It is very robust, and there is very good code. And therefore, everybody should know about it and use it in their research. Okay, for regression, it's one of the most powerful regression techniques. All right, and you will eventually get what exactly it means, but it takes a little bit of time. All right, and you will have a chance to practice with it today. Anyway, so the posterior probability measure was a Gaussian process. and that was good, okay? You can do with it whatever you want. You can actually sample functions from it, okay? Just like we did with the generalized linear model, we used to sample weights, and each weight corresponded to a different reality of what your actual function may be. Same thing here. The posterior measure specifies all these functions that are compatible with your prior knowledge and the data, and you can start sampling from them. And we'll do that later. But if you want a point prediction, if you just want to predict your function value at a single point, at a single new point, this little x right here, then you can derive a nice point predictive distribution, which turns out to be Gaussian. Of course, if everything is Gaussian, this is going to be Gaussian as well. And this point predictive distribution looks like that with a specific mean value. That mean value is the posterior mean function evaluated at that test input, and a specific posterior variance. And that posterior variance is basically the posterior covariance function evaluated at that test input. You just put that test input on both of its input variable arguments. Okay. And here's where these things are. So this posterior mean is this blue solid line that I have here. That's the mean of the posterior Gaussian process. And then that posterior variance, which is, again, there's the posterior covariance function evaluated at the same input, gives you the upper and the lower error bars. Okay, so I'm saying the mean minus 2 times the square root of that variance gives me the lower error bar. The mean plus 2 times the square root of the variance gives me the upper bound, and then I expect the truth to be between these two bounds. Okay? So that's what you can get and summarize your regression. And the things inside are samples from that posterior Gaussian process. So each one of these samples could be the truth, and you cannot really tell what is the truth unless you add some observations here and there. Okay, just to close this gap. Here, where you have enough observations, there's really no variability and no epistemic uncertainty. All right? Questions? Yes.
How do we get from the left part to the right part when we have a lot of observations to, or less observations to?
So this is just somebody gave you these observations, right? And it just happens that they are distributed like that. And all this is completely automatic. You say prior probability measure on the space of functions. Add these observations, Bayes rule, posterior probability measure on the space of functions. It just looks like that. Make sense? Now exactly what it does, I told you, it's a little bit complicated. Okay? I just told you what it does. Like 10 minutes ago. But it's okay. Yes?
Oh, like, how do we know if it's not overfitting? Because
this is why I'm advocating for this model, because it will not overfit. Okay?
like, it perfectly fits or
Yeah. So if your prior belief about the length scale is correct, then this is not overfitting. And I'll show you a way, if your prior belief about the length scale and the variance is a little bit vague, I will show you a way that will select the right length scale and the right variance, and it will still not overfit. Whereas everything else that you may be doing overfits. This is extremely robust. And that's why, even though it is very, very complicated to understand, because we go from a model, generalized linear model with like 10 weights that we found by maximizing the likelihood or by looking at the posterior of the weights or whatever, which is what you're doing in your homework. Now we're going basically to functions. Right? So instead of having like 10 weights, we have functions. There are infinite things. Yes.
How do you practically choose those points that you found?
So these points, they were just given by somebody to me. Okay, so somebody gave me some x's and some y's and just fit in the data. In practice, if you have, so the question is, how do you choose your inputs? All right. So another reason why I want to introduce Gaussian processes, even though it seems a little bit too complicated, is exactly because they give you a way to choose new observations. For example, you can use you can start with this data and then ask yourself a question: what x should I observe next? Where should I do my experiment next? And that depends on what you want to know. So you also need to say, I want to know the function as well as possible. You can say that. If you say that, then the answer you're going to get is go ahead and do the experiment about which your posterior Gaussian process is maximally uncertain. So it will tell you, go ahead and do this. And then once you do that, it will tell you, go ahead and do that. And then it will probably nail it. But if what you wanted, and we're going to talk about that in like 10 lectures. If you didn't want to find the function overall, but you wanted to find, let's say, the maximum of the function, just by looking at that, you can use the Gaussian process to ask the question, which observation will give me the maximum improvement, the maximum expected improvement to the current maximum that I see. So the current maximum that you see is here, right? Is this point right there. And you can ask the question, which x will give me the maximum expected improvement? Which is something that you cannot do. I mean, you can, but it's not so robust. And when you ask this question, it will basically tell you, you know what? There is a very small chance that this point may be the maximum. Like a very small chance. And if you're not satisfied by the fact that this small chance is small, okay, then you may go and do this experiment. And when you do this experiment, and you ask this question again, it will tell you, you know what? I'm 100% sure. I mean, depending on what you saw here, but let's assume for the sake of the argument that you do something here and you observe something there. Okay? And just imagine that this is added. And then if you ask the question again, it will tell you, you know what? There's no point that is going to improve upon the current best. So just stop. And then you can also ask questions like that for the minimum, right? If you ask here a question about the minimum, so the current minimum is this, and you can use the Gaussian process to ask the question, what is the input that will give me the maximum improvement to the minimum? So what is the input that is more likely to drive the minimum down? And it will probably tell you something in this region. And then if you add that and it happens to be here and you try to do it again, it will tell you, you know what, there's probably nothing that can improve upon you already have. But you can also do more complicated things, and we'll talk about that later. Okay, like probably the last lecture. Because it's not trivial. Yes?
Are we assuming that the noise is zero at those observation points?
Yes. So this is the assumption that I'm going to relax right now. Okay? So let's move to the next part, which is let's add some noise on our data. Okay? So let's now assume that our measurements are... So now this method, the method that I've shown you right now, interpolated. It actually went exactly through the observations without overfitting. This is the key. Okay, because you could interpolate with polynomials, but you would definitely overfit. Okay, so we start again by our x's, but now we don't observe f of x, we observe y, which is a noisy version of f of x. So we need to introduce our likelihood now, as we did before. Right? We introduce our likelihood, and our likelihood models the measurement process. So we say that when you try to observe something at x, you don't exactly get f of x, but you get something around f of x, and the way the value is kicked around f of x is with a Gaussian noise, additive Gaussian noise. Okay, so and this is our model. Of course, you could change this model and everything would change, but if you pick a Gaussian for the noise, then everything is going to still be Gaussian. Okay, but in principle, you can make it anything you want. You will just break down all the analytical formulas. And this is the noise variance, or the likelihood variance is the aleatory uncertainty of the measurement process. And you will see where this is going to go. So if you repeat my hand-waving argument of the beginning, start with some test inputs, arbitrarily distributed, arbitrary number, work out the posterior, and then find the corresponding Gaussian process measure, you find this. So you start with a prior probability, with a prior on your space of functions that is a Gaussian process. You add a likelihood model that measures that models the measurement process, and you include some Gaussian noise on that, and then you combine the two with observational data, noisy observational data using Bayes rule, and you get a posterior Gaussian process. And the posterior Gaussian process, has this mean and that covariance function. And if you look at this posterior mean, it's exactly the same as the mean we had before, only just has this sigma square added on the diagonal of the covariance matrix of your observed inputs. This is the only difference. This plus sigma square. And then if you look at the posterior covariance function, it's exactly the same as the one you had before, but it also has this change in the covariance matrix. And then if you want to go and predict, F, predict the function value, the posterior distribution is exactly the same as before. But if you want to go and predict y, which is what you measure, not what f is actually is, it's f plus the noise, then the point predicted distribution for y would be like that, with the posterior mean being this thing, and then the posterior uncertainty being basically this guy evaluated at x and x plus the aleatory noise. Okay, so here you see clearly the distinction between the epistemic noise, which can be reduced down to 0, and the aleatory noise, which is here to stay. Okay, and it would look like that. So now in this example, I'm going to use pretty much the same data set that I had before. Okay, but now I'm going to assume that there are different levels of noise. All right, so in the picture you see right here, I'm assuming that the measurement noise is 1. Okay, so of course, later on, I'll show you how you can actually fit the noise, okay, how you can automatically select the noise without overfitting. But now, just for the sake of the argument, sigma is fixed to 1, and I'm going to be reducing it. And just see how the prediction changes as you start decreasing the assumed measurement noise. So here you see the solid blue line is the posterior mean, and then the two standard deviations around the mean give you the lower and upper error bars, and you see a few samples inside from the posterior Gaussian process. And these error bars, by the way, include both the epistemic and the aleatory uncertainty, but these samples include only the epistemic uncertainty. Okay, so the samples will be showing you the epistemic uncertainty. So if I start the video, you will see the noise going down. I'm just selecting it by hand. Okay, so I'm saying, give me the best fit with noise of 1, give me the best fit with noise of 0.5, and smaller and smaller noise. And all these correspond to different interpretations of the same data set, right? If you really know that the variance of the noise is 1, this is the best fit you can get. If you really know that the variance of your data is 0.5, this is the best fit you can get, and so on and so forth. Okay? And you need, of course, something else to tell which one of these is the truth. Okay, you need something else. I'm going to give you this something else right now. But any questions so far? All right. So I don't think I need to make any of these points. So let's go back to, let's talk about how you can select that noise level. Okay, is there a methodology you can use to automatically select the noise level? And also there are the covariance parameters. So your covariance could have different length scales, different signal strength, as we call it, that allow, you know, depending on how far up and down your function can go. In general, the covariance function and the main function have parameters. Let's call them theta. Okay. How do you find these theta? This theta is the question I want to ask. And of course, the prior mean and the prior covariance have these parameters, theta, length scale, and so on and so forth, but you also have the likelihood model that has one additional parameter, this sigma square there. So you also want to be able to specify that sigma square. And the way we're going to do it is by putting a prior on theta and sigma square, using a likelihood and getting the posterior of these and doing something. Okay, so we're going to use basically the evidence approximation, if you remember. Anyway, with these assumptions, the likelihood of the observations is basically given by a multivariate Gaussian. And this is basically the definition of the Gaussian process combined with the likelihood process. I'll give you the chance to work these things out. Don't worry about it. And this is the only way you can grasp it. Seriously. I don't think you can. I can just put it in your mind if you just look at me. I think it's impossible. But we'll see how it goes with homework. Alright, so this is the likelihood, and then the missing ingredient is this. You need a prior on theta and sigma square. So you take all the parameters that you have and just say the best thing you can about them. Okay? And then you can do, you can write down the posterior of your parameters. So you can say, what should I think about theta and sigma after I see the data? And what you should think is the likelihood of the data given theta and sigma times the prior of theta and sigma. So this is just Bayes' rule. Okay? And of course here, you know, because this is not going to be analytic and it's not going to be Gaussian, there's really not a lot of things you can do right now before we learn about Markov chain Monte Carlo. There's not a lot you can do. But you can just maximize this guy. Okay, find theta and sigma by maximizing this guy, and this is gonna look okay. So instead of sampling from the posterior, which is the absolutely right thing to do and works always, and it's the most robust thing to do, and it retains all epistemic uncertainty, but it's not something that we can do right now without Markov chain Monte Carlo. The next best thing to do is to just maximize the logarithm of the proportion, the part that is proportional to the posterior, this part right here. Okay, by finding theta and sigma that maximizes this, you're effectively maximizing that. The only reason we work with the logarithm is because this is like 10 to the minus 6 times 10 to the minus something. It's something very, very small, and it doesn't make sense numerically to work with that. Okay? Alright, so this is how the parameters are selected. And all these are implemented in ZPy. And of course, most of the times we have absolutely no idea about the length scales and the covariance and the measurement noise. So we can just say, put a flat prior on them. Okay, we can just say flat prior for the length scales, flat prior for the variance of the covariance function, flat prior for the variance of the measurement noise. Flat. Okay, I don't know what it is. Flat. If you do that, then you will be effectively maximizing the likelihood. And that works also surprisingly well if you have enough data. And here's how this likelihood looks like for a characteristic example which I took from the Gaussian process book. So you have here the length scale of the covariance function, and you have here the measurement noise. And for this particular data set, there is a unique maximum for the likelihood. So the likelihood, the maximum likelihood technique is able to identify a single best length scale and a single measurement noise. Okay? But this is not always the case. This is a pathological case, actually. For other data sets, if you don't have enough, this is a good, nice point. If you don't have enough data, then the model cannot really tell what the truth is. But it can give you different versions of the truth without overfitting. So for example, for this is the same data set, right? So it's exactly the same observed inputs and outputs, and you try to fit them with Gaussian processes. And here on the top, you see the contour of the likelihood as a function of the assumed length scale and the assumed measurement noise. And for this particular set of observations, you see that the likelihood has two peaks, which correspond to two different interpretations of the data. So this peak right here corresponds to an interpretation of small length scale, high variability, and small noise, which is what you see here. So it says, okay, yeah, I could interpret this data set as if it comes from a source with a small length scale and a very small noise. But because I don't have enough data, let me just add this local maximum of the likelihood as well, which does the opposite thing. It interprets the data set as if it comes from a flat response with a lot of noise. And at this point, you can't really pick one of the two. Okay? And that's totally fine. And that's the magic of Bayesian statistics, that it does not force you to make the wrong choice, but it tells you here are the choices. If you have to pick, just know that I cannot pick myself. Okay? It's on you. This is what it tells you. And the only way to resolve this ambiguity is to collect more data. So if you collect more data, hopefully one of these will disappear. And it always does. I mean, you can always show that there's going to be a unique interpretation if the model is correct. Okay, if the model is completely wrong, meaning if your measurement noise is not really Gaussian, but it's something completely different, then it will not converge. But if you have picked the right measurement noise, it will converge. So this is one way to resolve this is with more data. Then it will definitely pick one of the two. Or by your prior knowledge. So maybe you know that this data set comes from measurements with an instrument that cannot have very big noise. Okay? And how can you tell this to the Gaussian process? Well, you go to the prior of the measurement noise and you say, well, it has to be something around there because I know that this machine does not have such a big of, does not add this much noise. So get rid of this. Just look at that. Okay, because instead of the likelihood, you would be looking at the posterior, and the posterior is likelihood times prior, right? And it will just kill the second local minimum. Or the other way around, right? You may know that this particular measurement process is extremely noisy, and then you change your prior for the measurement noise so that this one is killed. Okay? Yes?
What does the top figure mean?
The top figure is the contour of the likelihood as a function of the parameters of the covariance function, the length scale of the covariance function, and the measurement noise. This is what it is. Anyway, Perfect. We have 25 minutes to gain some experience with Gaussian processes. Finally, I managed to do it. If you haven't played with the previous version of the Gaussian process handbook, where you just took samples from Gaussian processes, that will be handbook number 10. What is the lecture number today? 11. All right, so if you haven't gone through handbook number 10, go first through number 10 and then start 11. All right, but please just know that in your research, especially if you're doing experiments, you will have to fit stuff, models to data. That's the best way to do regression. I know that it looks a little bit hard, much harder to understand than the generalized linear model, but it's the most robust way. It will certainly pay off if you spend the time to learn about it. Okay, there's some shortcomings, but let me not mention them today.